Hello, my name is Ilya, and I want to present results of SHREC 2021 track for classification in cryo-electron tomography. This is a joint work of 23 authors from 8 institutions across the world. Before discussing the benchmark, I want to provide background on the data modality and how the image is formed. Life exists at different scales, and we need different imaging methods depending on your goals. There are many methods, but each comes with its own pros and cons. Nuclear magnetic resonance spectroscopy, for example, can obtain 3D structure at atomic resolution, but only for small individual molecules. X-ray crystallography requires the sample to be crystallized, which changes the structure of the sample. How can we view the particles in its environment and without structural changes? Luckily, an approach called cryo-electron microscopy was developed. It's a combination of methods for which 3 scientists received a Nobel Prize in Chemistry in 2017. Jacques Debachet proposed a vitrification method that involves putting the sample on a thin grid and rapidly freezing it. With a fast enough cooling, water in the sample does not form ice crystals, essentially fixating the contents without breaking structures in the sample. The second Nobel Prize winner is Joachim Frank, who proposed an image processing optimization method to obtain 3D structure from 2D images. If the obtained micrographs contain thousands of copies of the same particle at random orientations, it is possible to calculate how they relate to each other, match them, and create a high-resolution 3D model. And finally, Richard Henderson, the third Nobel Prize winner, was the first person to actually achieve atomic resolution with cryo-EM in 1990. Since then, there were many improvements in detector technology and processing hardware. Now, cryo-EM researchers obtain atomic resolution structures almost routinely. However, what I described is known as a single-particle cryo-EM. Another approach that is considered by many as the next frontier is cryo-electron tomography. Instead of imaging a homogeneous sample with many copies, we can image entire complexes at varying tilt angles and computationally reconstruct a three-dimensional view of the region of interest into a tomogram. There are, however, limitations. For example, we cannot make projections all around due to the sample thickness at higher angles. This results in a missing wedge effect that decreases resolution. Another problem is sample interaction with microscope electrons. A dose too high will burn the sample, again decreasing the resolution of the tomographic reconstruction. One way to increase the resolution of regions of interest is to conduct what's called subtomogram averaging. Similar to single particle analysis, we can find volumes of identical particles, align them, and combine into a higher resolution 3D structure. Identifying and classifying structures of interest within complicated environments in noisy tomograms is a major challenge. Researchers come up with new methods to tackle this, but the comparison of such methods is problematic, and that brings us to the goal of this benchmark. With this work, we hope to support researchers developing new methods by introducing a novel, publicly available, and fully annotated simulated dataset. This should allow direct comparison of the methods and will hopefully provide insights for future research. We generated 10 tomograms with 12 different protein classes, gold fiducials and vesicles. For 9 of them, we provided ground truth annotations, such as class masks, particle locations, and the original sample that was imaged. There is detailed information about how exactly we generated the dataset in the paper. I think it is also to note that we hope this dataset can be useful for other cryo-ET method development, and not only classification and localization, but also reconstruction. For method comparison, we wanted to separately evaluate localization and classification, and used very popular metrics like precision, recall, and F1 score. This is a third edition of the benchmark. We are continuously working on our simulator. There are many technical details, and it is a bit out of the scope for the presentation, and you can find those details in the paper. There were 7 methods compared in this work. First one is URFinder by researchers from Purdue University. Their approach is to train 3 separate models. One is a U-Net semantic segmentation model that is used to localize particles, and then 2 ResNet models to find classified found regions. One ResNet model is specifically for gold fiducials, and the other is for protein classes. This approach is quite complex. After all, it's 3 separate networks, but it would be very interesting to see whether such specialized networks are better than one end-to-end network, for example. Next method is DeepFinder from India, Britain. It is based on UNet semantic segmentation and mean shift algorithm to cluster the segmented voxels into actual separate particles. It is quite efficient, and the authors really consider adoption of this method by cryo-ET researchers. There is a GUI tool that helps create 3D voxel level annotations, and it has been validated on experimental data in the paper. The third method is U-CLSTM, or UNet with convolutional long short-term memory decoders, from University of Missouri. It is a quite interesting idea to add LSTM memory units to UNet. The way I understand it, LSTMs should provide cohesion between patches of tomogram, making smoother predictions between patches. Or, in other words, long membranes or lamellas that are present in multiple patches should result in a much smoother continuous segmentation. The third method is MCDS-Net, or Multi-Cascade Denoising Segmentation Network, implemented by researchers from University of Patras. They adapted the idea from a UNet multitask cascade model, where each decoder path corresponds to one task with skip connections between decoders. In this case, they have two pathways, one for denoising and one for semantic segmentations, with skip connections between the encoder and from denoising to semantic segmentation. After the segmentation, they also do connected component analysis to localize individual particles. YOPO, or You Only Pull Once, is a one-step object detection framework by Carnegie Mellon researchers. They propose a subtomogram classification network, which they run on all possible tomogram patches, and then filter the obtained list to remove duplicates. The architecture of this classification network is quite interesting. It is designed to be transformation invariant, and one of the main advantages of this framework is that you only need particle location centers for training. CFN, or Central Feature Network, by researchers from Shandong University and Chinese Academy of Sciences, also is a subtomogram classification network, and also requires only particle centers for training. Their approach includes localization optimization, starting with random subtomograms. If a particle is detected, the process is repeated for a slightly moved subtomogram next to the original location. That creates classified regions around suspected particles, and with clustering, you can find one center location of such region. And finally, the last method we have evaluated was baseline template matching. It is used by cryo-EM research groups all around the world. Essentially, it is a cross-correlation between the template and tomogram, producing peaks where template matches the best, and suggests that the highest peaks are the particle centers. It is not an efficient algorithm, and you have to run it for each template / class separately. However, it is simple and can be run on GPU. There are two result sets obtained with template matching. One just naive approach of extracting top 1000 candidates, and the other approach is to filter out overlapping peaks. As mentioned before, we evaluate localization and classification separately for more insights. The column AD is average Euclidean distance from predicted particle center to ground truth particle center in voxels. The next columns are recall, precision, miss rate, and F1 score, which is a harmonic average of precision and recall. The paper has an expanded table if you want to see more details. We can see that, first of all learning-based methods are better at finding particles than template matching, the last two rows in the table. Judging by F1, DeepFinder is the best performer, followed by MCDS-Net, U-CLSTM, and CFN. For classification results, we have grouped the particle classes by their molecular weight. Small for particles less than 200 kilodaltons, medium up to 600, and large starting from 600. We can see that all large particles are well classified by all methods, including template matching. However, for medium and small particles, the differences are becoming more apparent. The best performers are DeepFinder, MCDSNet, and U-CLSTM, all producing very similar average F1. You can find detailed per class results in the paper. Now I'd like to focus on the insights that we have discovered with these results. First is the relation between particle size and F1 score. The x-axis in the figure is not scaled properly, but just sorted. We can see that there is a direct relation. Another confirmation that template matching, those two lines on the bottom, is performing worse than learning-based methods. There are a few notable extremes for template matching. For example, the jump at 560 kilodaltons is Rubisco, an enzyme that helps plants with photosynthesis. It has very distinct four-fold symmetry, and we believe this explains the sudden jump in performance. On the other hand, the other two sudden dips in performance are from classes that are quite spherical and without distinct features. Another way to confirm this correlation between size and performance is with confusion matrices. The classes are sorted by size, and we can see that in the upper left, the diagonal becomes quite blurred, while bigger classes in the bottom right are found easily. The amount of learning-based methods for cryo-ET will only increase in the future, so it is interesting whether we can find some insights for the future approaches. 4 out of 6 methods at least partly used unit architecture. It was originally intended for biomedical semantic segmentation and has proven record all over applied computer vision. Additions of multitask cascades like MCDSNet can really make it a very competitive approach. Moreover, there are dozens of modern UNet advancements like UNet 3+, UNet++, or U-CLSTM, for example. So if you have annotations for training such a network, we believe it is a very straightforward implementation and can be the first option to try. We can also compare models by their localization precision, a critical metric for accurate alignment and subsequent subtomogram averaging. I'd like to highlight 3 models, CFN, MCDSNet, and YOPO. They all show that they find particles better than template matching by about 1 voxel. CFN intentionally optimizes localization, and not surprisingly, it shows the best precision. MCDSNet incorporates denoising, removing noise, and that leads to a better precision. And finally, both CFN and YOPO include smart pooling approaches that maximize scale invariance, allowing to find particles of different sizes accurately. And final insight I want to share is the approach accessibility for cryo-ET practitioners. 3D semantic segmentation models require voxel-level annotations, which understandably is very hard to obtain, especially in the noisy tomograms. DeepFinder tries to minimize that by a separate GUI toolkit, but that is still suboptimal. YOPO and CFN, on the other hand, require only particle centers, which is very compatible with the current particle picking workflows that practitioners employ. We believe that gives them an edge in adoption. And all of the mentioned methods are supervised, even though, of course, everyone would prefer unsupervised methods. Some work has been done in that direction. For example, YOPO authors recently proposed a new method called DISCA, and it shows very promising results. We can also compare the speed of the methods. The methods were run on different hardware, but it still shows that the GPU-optimized template matching is at least 2 times and up to 50 times slower than inference of learning-based approaches. And finally, future work. We get a lot of requests to share our simulator, and we hope that this year we will finally be able to do that. And another point is that this evaluation was done only on the simulated data. We hope to add experimental validation next year, which should also allow us to address inevitable domain gap between simulation and practice. With this, I would like to finish the presentation. Thank you for your attention, and please feel free to contact me.